All right, so I'll just start by reminding you we have homework due next week. I graded the homework that was turned in to me, homework 5, those grades are up there. I haven't been posting solutions to that stuff because I've been trying to give people some leeway on turning that stuff in. So I apologize for that, but that's why I do have the solutions. I'm just being held up a little bit. So if you're one of the people who's waiting to turn something in, can you please do that soon so that everyone else in the class can see the answers here. I've also posted the chapter 6 notes. So today I think we'll finish up chapter 5 and we'll start chapter 6 on Thursday. And so the chapter 6 notes are on Blackboard. Please try to print those off before next class. I do want to actually watch those videos today. I know I've been alluding to them for a while and I keep running into other things here. I do want to look at the YouTube videos to give you an idea of how Fourier series work. But I want to just summarize what we have learned so far. So the next 2 pages here is a summary of everything in most things related to Fourier series, at least the general forms of them. So I just want to run through them. You know, the next 2 pages are like a nice reference for when maybe you're doing the final or when you're working on homework or something like that. And I just want to point out the differences between them. So the sort of the first thing we learned was this standard Fourier series, and that was specifically for a 2π periodic function. And so what that means specifically, we looked at things from -π to π. That's how we derived the formula in the first place. And that particular formulation had this function, right? And we talked about how to calculate the A's and the B's using these formulas. But the key thing to note that's different between these formulas and the other ones, well, first of all, they're inner products, right? And so they're integrals. But these integrals are all from -π to π because we're on the interval -π to π, right? And then inside the cosine and the sine is just nx. And then we've got pi's on the outside because we're on the interval -π to π. We then decided to extend that to functions that are size 2L. So instead of being specifically from -π to π like we were before, now we're trying to extend it a little further to functions on -L to L. And so rather than restricting ourselves to like the unit circle, for example, we can stretch things out beyond that point. And it has the same formulation, right? So we basically have a very similar looking Fourier series, except we've got L's in the bottom of our sines and cosines in all situations. And now, of course, our bounds on our integrals are from -L to L because we're on a different interval, right? And of course, we have L's over here as well. And so it looks very similar. We just did like a substitution where we extended this to things a little bit past -π to π. And so those are the 2 main takeaways. And then we kind of moved it a little bit further and said, oh yeah, we noticed actually anytime we did an even function, it only had cosines, and sines, and whenever we had an odd function, it only had cosines. And so that led us to the sine and cosine Fourier series, which is just the exact same thing we just did on the last couple pages again, except we're only looking on 1/2 of the interval. And we're using those calculus topics to sort of evaluate these things, right? So we stick from 0 to L, but then we double the size of the integral because we have an even function, for example. Or the one down here, we're going just on 0, 0L, but we have just cosine in the cosine series. And so just kind of summarizing those specific versions of these Fourier series. Again, these are for odd or even functions specifically. And so those are the 4 formulas that we've derived throughout the section. I just thought it'd be worth like putting them all in one place instead of having them spread across like 2 or 3 sections. And then before we watch the video, I just wanted to relate what we did to things we've already seen. So this is sort of listing how Fourier series are actually projections, right? And that's why we spent a lot of time early in the course talking about projections and looking at projections in Rn, and then looking at projections in polynomial spaces before we actually moved on to Fourier series themselves. And so with that in mind, when we look at the Fourier series, which is, again, is given by this, for example, this is the cosine series, we're actually doing a projection onto a vector space using these basis elements. And we had shown in a homework problem that this is a basis because these are linearly independent. And so in that sense, we're doing a projection, right? We're projecting sines and cosines onto a piecewise function. And in terms of the sine and the cosine series, they have sort of a reduced version of that basis is all that's saying. And the coefficients, the Fourier coefficients, which is given on the last page, those are sort of the function representations of those basis items. So what we're doing again with the Fourier series is we're projecting these sines and cosines onto a at least piecewise continuous function. And we've seen it, so it's doing it by hand. We saw it in Maple a little bit. And when you extend it to things that are not piecewise, or sorry, not periodic, that's what's called the Fourier transform. And then that's when this stuff gets really useful. And so I just want to show a couple of videos that I just popped on YouTube and found a couple what I thought were interesting videos. Excuse me, related to the Fourier series that have like nice graphics and things like that I thought would do a better job of explaining it than I would. So I'm just going to take a second and share my screen and maybe watch a couple of them. This should take us close to maybe 10 minutes, I think. So there's 3 videos. One's 5 minutes, one's 4 minutes, and one I just want to show a picture from. So this will take us approximately 10 minutes, and I'm going to sort of comment on the video as it goes, where I think it feels right. So I'm sharing my screen now, and I'm sharing this YouTube video. This is a video that's in the playlist. It's in the Math 3500 playlist. And so I'm just going to play it and stop it a couple times to talk.
There are these things called Fourier series. In a manner of speaking, they're a way of taking a complicated whole and viewing it as a sum of its simpler parts.
Can you hear that okay, guys? Is it loud enough?
It's a little quiet, and it's also pretty stuttering.
Is it like blurry?
It's not blurry. It's not like when you were playing it before. It was like really laggy. I don't know if it's because
maybe it just needs to catch up. Someone else going to say something? The sound is also, I think, not aligned on this particular video, but it doesn't matter once
there
they get off.
There are these things called Fourier series. In a manner of speaking, they're a way of taking a complicated whole and viewing it as a sum of its simpler parts instead. Fourier series facilitate models of natural phenomena. Ancient Greek astronomers theorized that the Earth lay at the center of the universe, with the moon, sun, and heavens rotating around it in perfect circles. However, when they looked into the night sky and observed how the moon and planets were really moving, they realized that the motion was inconsistent with their theory. Taking the moon, for example, if the moon was moving in a circle, like in the Greeks' theory, it should always be the same distance away. So why did it appear darker on some nights and brighter on others? It was also bigger on some nights and smaller on others. The Greeks had to change their hypothesis then. What if for each heavenly body there was a smaller circle rotating around a bigger circle, and the body was rotating on that smaller circle? But again, what they saw in the night sky just didn't match up. So the astronomers started adding circles on circles on circles, until they had a model of celestial motion that matched what they saw in their observations. It's known today that orbits are ellipses, not circles on circles. So how did the Greeks' incorrect theory match what they observed in the sky? The answer is Fourier series. Adding up the many circles, the parts, allowed the Greeks to model celestial motion, even without understanding the true elliptical paths.
So just to clarify here, back in the day, they thought that the Earth was at the center, of the universe, and they were trying to figure out a model that would actually fit their observations. And they kept adding these circles and these circular motions until the things that they saw matched their model. And this is going to relate to Fourier series in just a second here.
Up the many circles, the parts, allowed the Greeks to model celestial motion, even without understanding the true elliptical paths. In math, orbiting around in a circle can be represented as the orbit is equal to r times e to the I omega t.
Let me also just clarify, they're going to start using this equation, r to the ei omega t, which we've seen before, but we've mostly been using sines and cosines, right? But we've seen several times how you can take sines and cosines and write it as this e to the I omega t thing. And so they're going to be talking about e to the I omega t, but you can see they're going around a circle, which is just doing sines and cosines. So you can think about e to the I omega t as the basis elements. Just want to mention that.
Where e to the it represents moving in a circle. The Greeks in their theory, though, had circles of different sizes and rotation speeds. This is where the other variables come in. The r represents radius and controls how big the circle is. The omega represents angular frequency and controls how fast the circle rotates around. Representing circles rotating on circles is simply adding up more of these terms. When we add more and more, reaching an infinite number of circles, we now have what is called the Fourier series of the orbit.
Right, so that thing right here, this sum of the e to the I thing, that's the Fourier series represented as the exponent, the natural exponential.
We now have what is called the Fourier series of the orbit. Ultimately, the Greeks weren't right about how orbits worked. What they ended up doing was constructing a Fourier series approximation of the real elliptical orbits. Sure, Fourier analysis can create an ellipse approximation, but it can create really any shape too. The right arrangement of circles can make an orbit in the shape of Homer Simpson's face. Something important to note is...
And so what the thing you should take, first of all, one thing is, I think it's so interesting is how, rather than just thinking about what was actually going on in the world, they came up with this really complicated Fourier approximation of what was actually going on. So they made it much more complicated than it needed to be because they were trying to like force reality into what they believed. But they ended up doing Fourier series, which is interesting. And what you should take away from this kind of quick Homer Simpson thing is you'll notice all the circles spinning around each other in a similar way. And what's going on is the center of the smallest circle on the end is tracing out Homer Simpson. And so what they're going to talk about in a second is how you can take images and represent them as some Fourier series. And that Fourier series you can think of as creating these circles. And so I just want to sort of summarize that before we see it in practice here. Let me back up and let them say that again.
Fourier series approximation of the real elliptical orbits. Sure, Fourier analysis can create an ellipse approximation, but it can create really any shape too. The right arrangement of circles can make an orbit in the shape of Homer Simpson's face. Something important to note is that an orbit can be thought of as anything periodic. That is, something that repeats itself over time.
Right, so these are the kind of graphs we've been looking at a lot, these periodic functions.
So Fourier series can take anything periodic, like a waveform, and analyze it as sums of circles. From the unit circle, it's also known that circles are basically sines and cosines. Taking these two ideas together puts Fourier series in its more familiar form, as sums of sines and cosines representing waveform.
And so that's a kind of, I think this is an interesting sequence here that you should also just kind of see what's going on. They're adding up a bunch of different sine and cosine waves, and every time you add a new term, it changes the shape of the wave. And we know the more terms you add, the better approximation you get. And so that's what's going on in this situation. They're decomposing that more confusing looking shape into a sum of repeating patterns. So when you add these four things together, you get the more complicated looking shape.
It's Fourier series in its more familiar form, as sums of sines and cosines representing waveforms. A lot of complex nature can be represented this way. The planets are not the only example. While Fourier series allowed a human civilization to model and simplify nature, it also allows nature to model and simplify nature. Your own body is performing Fourier analysis just listening to this video. Ears make Fourier series to process sound. Inside the inner ear are thousands of hair cells of varying lengths. Because the hairs are different lengths, they resonate at different frequencies. For example, long hairs will pick up waves with lower frequencies, and short hairs will pick up waves with higher frequencies. When a complex sound wave enters the ear, the hairs help the brain break it down into individual frequencies. Instead of the total sound wave then, the brain sees a bunch of simple sinusoids with different amplitudes and frequencies, and then combines them to process sounds. Rather than taking the actual sound wave as a whole, the brain is able to process the same information by analyzing individual sinusoids. Just like how the Greeks understood planetary motions as individual circles rather than actual ellipses. Behind the equations of Fourier series lies a means of representing many aspects of nature. The Greeks unintentionally used Fourier series to simplify their science. They didn't understand the true nature of orbits, but were still able to use sums of circles as a matching model. At the same time, the human body creates Fourier series naturally and subconsciously. Rather than processing the true sound wave as a whole, the brain is able to process sound using individual sinusoids. Fourier series are everywhere, and ultimately they're tremendously...
So I'm going to stop the video right there, and maybe just transition right over to this other one and give you the general idea here. And this one's not that long, actually. Let's watch this one too. So this one's going to specifically talk about how to use Fourier series to do signal processing. So it's going to expand on the idea of the sound wave idea, or reducing noise in a picture or an image. So, you know, when this video here was talking about the brain picking up different signals or sound waves, you can kind of think about that as like when you listen to something that has a really high-pitched sound in it or something, you might pick out that one individual sound. And if you wanted, you know, sometimes you can download like or at least this used to happen more when you were sort of ripping stuff offline. But when you download music offline, sometimes it has artifacts from the download process, like high-pitched noises or like background sounds or like crackling or whatever, and you can pick that up with your ear. And we can also use Fourier series to pick it up and remove those imperfections. And so that's what this video is talking about a little bit.
Look at this photo or listen to this recording. What do these two have in common? The photo contains specks of light called noise. The voice recording also contains background noise. In the real world, professional software is used to minimize these kinds of noises. Programs like Audacity and Lightroom work using something called signal processing, which uses a mathematical technique called the Fourier transform.
So the Fourier transform is an extension of the Fourier series. Fourier series is specifically for periodic functions. Fourier transform is used for non-periodic functions. So keep that in mind as they're talking here.
Signal processing is the technique of processing a signal to isolate or obtain the more useful information, such as the recording of a voice, and to remove unwanted information, such as the background noise. And since a signal is essentially any waveform that is a function of time, signal processing is not limited to photos and voice recordings. Signal filtering works using a system called an LTI, or a linear shift invariant system. Such a system has two simple properties. Firstly, as implied by the name, the system has to be linear. That is, if we input this red wave and this blue wave separately into the system and obtain the corresponding two outputs, then if we input a sum of the red and blue wave, we will get a sum of the two corresponding outputs. This is called the superposition principle. Secondly, it has to be time invariant. Suppose we input this blue wave now and get the corresponding output. Then if we input this blue wave 1 hour later, we should still expect to get the same corresponding wave. This symmetry in line, described by Noether's theorem, is important because it conserves the total energy of the input wave function.
Let's see how the LTI system works to filter some background noise. Suppose we have a recording of a voice, but mixed in the recording, there is an undesirable low-frequency hum in the background. We would take our sound recording.
So just to be clear, this is like a sound wave And if you've ever recorded music or something and you put it on your computer, right, you get like a bunch of different sized waves depending on the frequency and things of what you're looking at. And so you can basically pull apart the different instruments, for example, in a song or something like that, or different voices if it's like two people talking on like a radio show or something like that. Or in this case, you might have the thing you want, which might be a song, which is the black, and maybe the red part is some background noise or some artifact of downloading it or something like that. And we want to get rid of the red part, basically, right?
Desirable low frequency hum in the background. We would take our sound recording and pass it through the LTI system, which in this case can be an auto filtering application. Then, in this application, we apply a filtering function, such as this one, to the recording. If we superpose these two wave functions, we get a new recording that only has the high frequency recording that we want and does not have any undesirable low frequency hum.
Physically, the LTI system works because of the impulse function, also called the Dirac delta function. When a wave function, or we call it a signal, is passed through a system, we apply the impulse function corresponding to the specific signals that we want.
But wait, we said earlier that the recording we have is a function of time. So then, how do we separate the different sound frequencies to isolate the sound that we do not want? The solution comes from a mathematical technique called the Fourier transform. In 1822, Joseph Fourier published his work on heat flow, in which he showed that the functions of a variable can be converted into a series of sinusoidal functions. This was originally used to convert periodic functions to a sum called the Fourier series. Later, it was generalized to non-periodic functions using the Fourier transform.
So then, when we apply the Fourier transform to our sound recording, we can decompose one recording into the various frequencies that it was originally composed of. Then, it will be easy to isolate the frequencies that are undesirable and apply our audio filter to remove them. Once the filter is applied, the inverse Fourier transform is applied, and we get back our sound recording as a function of time.
So just to clarify one more thing there.
Rather than taking the actual sound wave as a whole,
the brain is able.
Is anyone a musician? I feel like, Danny, do you play an instrument? I don't know why I think that for some.
Yeah, a little bit.
Do you ever record? I don't know, it doesn't really matter, but you might be more interested in this if you were like experienced with sound waves, is what I was sort of thinking. Is anyone else playing an instrument? Anyone else in here? What's I gonna say? And so the other thing I'll just maybe mention, I tried to find a video on this and I wasn't able to find a good one, is we know the Fourier series, right? We know the Fourier series because it can be used on periodic functions. So it does the same thing over and over and over again. The Fourier transform, which there is some information at the end of our textbook about the Fourier transform, you can see can be used to approximate non-periodic things. And so a song or something like that, like when you download a song, it's going to be non-periodic. Like when you put it into some music program and you looked at the sound waves, it would look something like this, where it's not just the same thing repeating over and over again. I mean, there might be parts that repeat or instruments that repeat, but the song itself is going to be non-periodic. Well, if the Fourier transform can approximate those non-periodic waves, what you can do is you can represent a song using a Fourier transform, which is how we're able to compress MP3s and make them smaller to save. So like if you wanted to email your friend an MP3 or put it on a thumb drive or something, you compress it, right? Well, when most compression softwares will actually just take the song and represent it as a Fourier transform. And so rather than recording all the different sound waves and all the instruments, it instead represents them as a function. So it's much easier to store, in other words. And then when you unpack it or you unzip it or whatever you call it, it recreates those sound waves again using the function. And so that's sort of another high application of these Fourier transforms is in compressing music. Or you can do the same thing with an image, right? Image compression is also just the same thing. The last thing I just wanted to show you to drive the point home, I'm just going to show this image. I'll let it catch up here. Is the idea that, you know, when you hit a tuning fork, if you know what that is, like if you're trying to tune your guitar or something, it gives you some sound, like the letter or the note C, which might be represented on the left here. But when you strum a guitar string, the sound that comes out is a composition of harmonics. And so it's not just like one tune coming out, it's a bunch of different combinations of sounds. And what you actually hear, the final guitar note, is the combination of all those things. And so this is just reiterating that the sounds you hear are sort of these repeating, oscillating periodic waves that can be decomposed into their individual components. And these individual components would be like the terms in a Fourier series, for example. And so that's sort of, I mean, there are some lower level applications of Fourier series that we're looking at in the homework, like just approximating functions or finding the value of a convergent series or something like that. But the sort of the big picture Fourier series application things are in these signal processing, image compression type things that are beyond the scope of our class. But I'm hoping that if it interests you, you definitely have enough basis after this class to pursue it in a different upper level or graduate level class. Okay, I'm going to stop sharing my screen, but are there questions about the video or anything I just said there that I can answer before we get back to the notes? Okay, so let me stop sharing my screen here. And I'm going to put the next page of the notes up. So these are sort of, like I said, the low level kind of applications that we're going to see of the Fourier series. You know, Fourier series or Fourier transforms are sometimes their own class. I've seen, you know, Fourier transform class in grad school, for example, where you really might get into the nitty gritty of some of this stuff and learn how to actually like compress images by hand and things like that. So if it interests you, keep that in mind. The thing we're going to look at in this page, which there's a homework question about this, is using Fourier series to, for example, show that the sum of 1 over k squared, the infinite sum, right, this infinite series, converges to pi squared over 6. And so we're going to do that specifically by looking at the cosine series of the periodic extension of x squared. And so what we're going to do basically is we write down this Fourier series. It's going to involve the sum of 1 over k squared, and we're going to be able to show that that equals pi squared over 6 using things we know about the Fourier series. So let's think about what this looks like first. So x squared on 0, 1. That's 0 to 1, let's say. And x squared does this, right? And so there's x squared from 0 to 1. And if we did the periodic extension of that in both directions, it would just end up looking like this, right? So that would be the extension from -1 to 1. And if we just copy and paste that over and over, it's just going to be like this repeated u kind of in both directions. And so we're going to find it's even, right? It's an even function because this has y-axis symmetry. And so that's why we're looking at the cosine series, because it's an even function, and we know even functions only end up having cosines in the Fourier series. So that's why we're looking at the cosine series. And we're going to write down what the cosine series is, which I'll just remind you is on the last page here, right? So we know the cosine series is given by this, and we need to calculate a0 and an. So that's what I'm about to do right here. And so we know our Fourier series, I'm just going to write down that formula, is this. Right, so L is 1 in this case because we're going from 0 to 1. And then we know the formula for a0 and an, right? So a0 is going to be 1 over L, integral from 0 to L, x squared dx. I'm literally just writing down these two formulas here. So I'm going to use that formula first. That's a nice, easy one to do. We just do x cubed over 3 from 0 to 1, and we just get 1/3. So the first coefficient is 1/3. The second one's a little bit more work because we're going to need to use tabular integration, but the AN formula becomes this. Again, just using that formula on the last page. And again, this is a classic integration by parts question, right? You've got x squared times cosine. And so we would use tabular integration. And so just to be clear, I'm going to skip right to the answer here, but I'm going to use tabular integration here and obtain this. And I don't have a lot of room, but I am going to try to cram in another term here. 2 sine n pi x for n cubed pi cubed. And this needs to be evaluated from 0 to 1. There's a parenthesis right there. Okay. And so I'm actually going to plug those numbers in and then try to rationalize what we get. So when you plug a 1 in, you get this sine n pi over n pi. Let's see here. Right. Plus 2 cosine n pi, n squared pi squared. So just plugging a 1 in so far. And then plug a 1 in here as well. And so that's what you get when you plug a 1 in. And when you plug a 0 in, all the terms go away. Because you get a 0 and the x of those two things. So those two things go away. And then sine of 0 is 0 as well. And so you only get the terms when you plug a 1 in. Just going to pause right there and see if that integral looks okay. If anyone has a question about that integral or tabular integration. Based on the homework, it seems like people get tabular integration just fine. But if you have a question about it, happy to clarify. Okay. So let's see what these ones equal. Sine of n pi. So n is an integer, right? So plus or minus 1, plus or minus 2, or 0, or whatever. And at all, so this is like multiples of pi. At all multiples of pi, the y value is 0. And so sine of n pi equals 0 for all n. So it doesn't matter what n we plug into sine of n pi, we get 0. And so that's the case with this one too. And then we've seen cosine n pi a bunch of times already. We know that cosine of n pi bounces back and forth between -1 and 1. And so we can represent cosine of n pi. So I'm going to factor out the 2 over n squared pi squared part, and then the cosine part becomes plus or minus 1. And so you can do -1 to the n. And so when we simplify that all down, you just get this term multiplied by 2, and so you get 4 of that one. So this ends up being 4 over pi squared n squared minus 1 to the n. So that's our AN coefficient. Again, just going to pause there and see if there are any questions. Again, the homework that's due next Thursday. I haven't had a lot of questions out, so I'm assuming people haven't maybe started working on that one a lot, but it's a lot of like doing these kinds of figuring out the Fourier series and doing, well, one of them is doing almost exactly this. So is that okay? Okay. So let's write down the cosine series. right? So, I mean, we wrote it down. It's this thing with an being this. So it's going to be like 1/3. This is going to go in there. Let me just write it down first. And then you can see we're going to evaluate it at x equals 1. But we're going to evaluate at x equals 1 for a reason. So let me write down the final series, and then we'll do that. So the final series that we just found was f of x equals, let me slide this up a little bit, 1/3, that was our a0, plus the infinite sum of 4 over pi squared n squared minus 1 to the n. That was our an coefficient that we just found. And then it's a cosine series, so we have cosine n pi x. Questions so far? All right. And so we're being told to plug in x equals 1. So that must matter for some reason, right? And I think that's the way it works in the homework too. Let me double check what the homework question is, just so I make sure you're going to be properly prepared for that. I'm just looking at the homework. Where'd it go? So one of them, yeah, so it tells you to do x equals 0, for example. And so we're being told to use x equals 1 here. Anyway, so then I'm just trying to say the homework problem is very similar. So on this particular one, we're going to plug in x equals 1. So at x equals 1, so I'm going to plug in x equals 1 to here. Right? F of 1 is 1/3 plus this sum 4 over pi squared n squared minus 1 to the n. And then when you plug a 1 in here, it just becomes cosine n pi again. Oops, can't spell cosine though. Cosine n pi. And we know that cosine n pi is minus 1 to the n again. We keep seeing that over and over and over again. And so really, this becomes 1/3 sum n equals 1 to infinity 4 over pi squared n squared. And then we have minus 1 to the n times minus 1 to the n. And so that is minus 1 to the n squared, which is 2n. I don't know if people like that or not. Let me maybe show the detail there. When you do minus 1 to the n times minus 1 to the n, you add the exponents, right? Like bases, different powers. So you do minus 1 to the n plus n, which gives you the 2n. And moreover, you could think of minus 1 to the 2n, like I said before. It's like minus 1 squared raised to the n. What's minus 1 squared? Anyone out there?
Just 1.
That is 1. Thanks, Danny. Glad you're there. And so minus 1 squared equals 1. And so this is just 1 to the n. And so this really just equals 1. In other words, this term just goes away. It just becomes the number 1. And so the Fourier series really simplifies to 1/3 plus the sum of n equals 1 to infinity of just the 4 over n squared pi squared part. Right, and so we just showed basically that f of 1 equals that. And this has this like is starting to look sort of kind of like what we're gunning towards, right? We're trying to show this thing. Trying to show that 1 over k squared summed up equals pi squared over 6. And we've got like a 1 over k squared and the 1 over n squared here. And so we can almost get the answer here. Question so far before we finish it off? All right, so then to finish it, we look at the Fourier's convergence theorem. And so the convergence theorem says that a function will converge to either the function value or the average of the left and the right limits. So that's this thing here. This is on page 18. Right, we're on page 18 of these notes. This is the Fourier convergence theorem. And so it says that the Fourier series will converge to the function value itself if it's continuous there, or if it's not continuous, you do the left and right hand limits. Well, this function is continuous there, right? So our f of x is continuous because it's just f of x is x squared, and so it's continuous at 1. And so at 1, the Fourier series is going to converge to the actual function value. And so by the Fourier series convergence theorem, so by, I'm going to call this the FCT, Fourier convergence theorem. By the Fourier convergence theorem, at x equals 1, the Fourier series converges to little f of 1, which is just 1 squared, which is 1. In other words, we have two expressions for f of 1. F of 1 equals this by the Fourier series, and by the convergence theorem, it equals this. And so we can set those two things equal to each other, and then that's how we're going to get our answer. So let me make that note in case that's not clear. We have two expressions for f of 1 set equal to each other. So what we just found was 1 equals this thing, 1/3 plus that sum. And then if we just rearrange this thing, we get our answer. So I'm going to subtract the 1/3 over to the left. And then this sum only depends on n, right? So I can pull the 4 and the pi squared in front of the sum. In other words, I'll do this. 2/3 equals 4 over pi squared times the sum of 1 over n squared. And we now almost have the answer, right? 1 over n squared is the thing we want to get by itself, right? We're trying to show that 1 over k squared, which is the same as 1 over n squared, equals this. So let's get that sum by itself. So let's multiply by pi squared, divide by 4. And when you do that, you get pi squared over 6 equals that sum, which is exactly what we were trying to show. So I don't personally view this as like some amazing application of Fourier series. It's kind of like, hey, if you've got some infinite sums inside your Fourier series, then you can use the convergence theorem to figure out what that infinite sum converges to. I don't think those applications are terribly bountiful, but it's kind of nice, I guess. Shows something you can do with the Fourier series. I mean, questions? Anything about that? Okie dokie. trying to decide whether I want to try to cram the next 3 or 4 pages in here. I also want to do a maple thing. I think I'm not in a particular rush here. And so I think I'm just going to maybe end a little bit early here today and not try to rush this section. Can I answer some questions about what I've shown on this page? So looking ahead and looking at the homework, there's just one other thing we want to show that applies to the homework especially, which is showing the error of a Fourier series. And so there's a couple questions at the end especially that ask about the error. And so we do need to look at that before you can finish the homework, but you can do almost all the homework questions, I think, at this point, especially using the Maple code. Please do use the Maple code to do the Fourier series of those things. You're doing at least a couple of them, 2 or 3. And you're asked to plot them too. So obviously, hopefully you're going to use the Fourier series to do that. Again, though, I'm not going to rush this next part. I'll just take my time on it on Thursday. Can I answer some questions? Anything you guys want to talk about? Okay, maybe by then, if you wouldn't mind looking at the homework too, that'd be good, because I think it definitely won't take the whole period to finish this section. And then if you have some questions about the homework, I'd be happy to maybe not work them out for you, but we could like look at the Maple code you should be looking at. You could try them while I'm on the call. Anyway, maybe getting some questions together for the homework would be good too, so we could spend some time on that on Thursday. Thoughts, questions? Kwasi, you there?
Yep.
All right. Bradley? She's there. How about Nick? Wonderful. You guys are so there. All right. Thank you for being there. I'll see you guys on Thursday. Have a good one.